Remember, sometimes less truly is more. Neural networks come in many flavors, each designed for specific tasks. Feedforward networks. Basic networks where data flows in one direction. Like an assembly line, each worker does their job and passes it forward. Use includes classification, regression, and simple pattern recognition. Convolutional, or CNN. Specialized for processing images and spatial data. Like how your eyes scan a photo, looking at small patches, and building up understanding. Use includes image recognition, computer vision, and medical imaging. Recurrent, or RNN LSTM. Has memory to process sequences. Like reading a book, you remember previous chapters to understand the current one. Use includes text processing, speech recognition, and time series. Transformers. Uses attention to focus on relevant parts. Like a smart student who knows which parts of textbook are important for the exam. Use includes language models like ChatGPT and machine translation. Each architecture is a specialized tool for different problems. Clustering evaluation is tricky because there's no single right answer. The challenge. Unlike supervised learning, clustering has no right answer to compare against. Like judging art, no single correct way, but we can measure different aspects of quality. Two types of evaluation include internal, using only the data itself, and external, comparing to known ground truth. Evaluation metrics. Internal metrics include silhouette score for how well separated are clusters, inertia for how tight are clusters internally, and Kolinsky-Harabas for ratio of between within cluster variance. External metrics, when true labels exist, include adjusted RAND index for agreement with true clusters and normalized mutual information for shared information. Now, let's look at the pro tip section. Always visualize your clusters. Numbers don't tell the whole story. Good clustering tells a meaningful story about your data. Two fundamentally different approaches to learning. Batch learning. Train the model using all available data at once, then deploy it. Like traditional school, you study all semester, take final exam, then graduate. Characteristics include uses entire dataset for training, model is static after training, need to retrain completely for updates, and computationally expensive, but stable. Best for stable environments, large datasets, and high accuracy requirements. Online learning. Model learns continuously from new data as it arrives. Like learning to drive, you keep improving with every trip, adapting to new roads and conditions. Characteristics include updates model incrementally, adapts to changing patterns, lower computational requirements, and can forget old patterns with catastrophic forgetting. Best for streaming data, changing environments, and resource constraints. Now, let's look at the hybrid approach section. Many systems use mini-batch learning, small batches processed frequently. Choose based on your data's nature and business needs. Selecting the right algorithm is like choosing the right tool for the job. Data size and type. Small data works with simple algorithms like linear and naive Bayes. Big data needs scalable algorithms like SGD and random forest. Like choosing transportation, bike for short trips, airplane for long distances. Interpretability needs. High interpretability uses linear models and decision trees. Low interpretability allows deep learning and ensemble methods. Medical diagnosis needs explanation. Movie recommendations don't. Performance requirements. Speed priorities use linear models and naive Bayes. Accuracy priorities use ensemble methods and deep learning. Race car versus luxury car, different priorities. Problem type. Linear problems use linear regression and SVM. Nonlinear problems use tree-based and neural networks. Straight roads versus winding mountain paths need